Let's look into the 12th question. You want to design a unified pipeline to handle both batch and streaming data while maintaining historical snapshots and auditability. Which Delta Lake feature is essential? Here are your options. A. Time travel allows querying previous versions of data for auditing and debugging. B. Schema enforcement ensures no new data appended if schema differs. C. Memory and disk caching optimizes repeated computations of streaming data. D. Coalesce reduces partitions to avoid small files during writes. You might be wondering why we even need something like this. I mean, if you already have your batch and streaming jobs running, why would historical snapshots or auditing even come into play? Let's break that down together. In any real-world data pipeline, you're not just processing data and then forgetting about it. You often need to answer questions like, what did my data look like yesterday? Or, can I reproduce the results of an experiment I ran 2 weeks ago? And that's where Delta Lake really shines. Unlike traditional storage formats, Delta Lake keeps track of every change made to your tables. Every insert, update, or delete is versioned automatically. Option A is time travel. And honestly, this is the feature that makes everything possible when it comes to auditing and tracking historical snapshots. Imagine you made a mistake in a batch job last week. Without time travel, you'd have no easy way to see what your table looked like before that batch ran. You'd be stuck trying to figure it out manually, and that can get messy really fast. But with time travel, you can literally query the table as it existed at any point in the past. You can even reproduce experiments or debug issues by seeing the exact state of your data at that moment. Option B is schema enforcement. Now this one's important. Don't get me wrong. Schema enforcement ensures that if someone tries to append data that doesn't match the existing schema, Delta Lake will reject it. That's fantastic for data quality because you don't want random columns or mismatched types creeping into your tables. But here's the thing. While it's great for keeping your schema clean, it doesn't actually help with historical snapshots or auditing. It's more about validation than history. Then we have option C, memory and disk caching. This is a performance optimization. It can speed up repeated computations, which is super useful if you have queries that run over and over again. But it doesn't help you answer the question of what did my data look like last month? It's a tool for efficiency, not for historical tracking or auditability. Option D is coalesce. This one's about managing file sizes. Delta Lake writes data in partitions, and sometimes you end up with a lot of tiny files. Coalesce helps combine partitions so you don't have thousands of tiny files clogging up your storage. Again, very useful for performance and managing storage, but it doesn't give you historical snapshots or auditing capabilities. If your goal is to have a robust pipeline that can handle both batch and streaming data while keeping a clear history of everything that's happened, there's really only one feature that nails this perfectly, and that's time travel. By leveraging time travel, you're able to query any previous version of your data, which is exactly what you need for auditing, debugging, or reproducing experiments. In the context of the Databricks Certified Data Engineer Professional exam, questions like this aren't just testing whether you've memorized features. They're testing whether you understand how these features are used in real-world scenarios. Auditing, historical snapshots, reproducibility. These are things that matter in production, not just on paper. And time travel is literally designed for that. Think of it this way. Without time travel, if something goes wrong in your batch or streaming pipeline, you might have no way of seeing what happened. You'd have to rely on logs, or worse, try to reconstruct data from scratch. But with time travel, you can go back in time, like a versioned record of your table, and see exactly what your data looked like at any point in the past. That's incredibly powerful, especially when you're dealing with complex pipelines that combine streaming and batch workloads. And let's not forget, combining time travel with schema enforcement is actually a best practice in production. Schema enforcement keeps your data consistent, and time travel keeps your history intact. Together, they make your pipeline both robust and auditable. To wrap this up, the key takeaway is this. When you're building pipelines in Delta Lake and you care about auditability and historical snapshots, which you absolutely should, time travel isn't just a nice-to-have feature. It's essential. It lets you query previous versions of your data, reproduce experiments, debug issues, and maintain trust in your data pipeline. We're diving into a real-world scenario that's going to test your skills, and trust me, it's one you'll want to nail. Picture this. You're creating a materialized view in Lakeflow declarative pipelines to aggregate data for analytics. The view needs to filter out records with missing year values and sort artists by song count. But here's the big question. Which feature ensures efficient updates while maintaining correctness? Let's look into the first question and figure this out together. All right, let's lay out the options we've got. We're talking about materialized views, SQL views, streaming tables only, static delta tables with full refresh. Now, this one's really interesting, so let's break that down together. We're building this materialized view, and the goal is to make analytics smooth and efficient. Filtering out those missing year values means we're cleaning up the data right from the start, only keeping what's useful. Then, sorting artists by song count. That's all about giving analysts a clear, organized view to work with. But the real challenge is making sure this view stays up to date without breaking under the pressure of new data coming in. You might be wondering why this happens. Well, it's because data pipelines are living, breathing systems, and they need to handle changes without slowing down or messing up the results. So, which of these options fits the bill? Let's start with materialized views. These are like the superheroes of data storage in this context. They cache the computed results, which means once you've done the heavy lifting, like filtering out those missing years and sorting by song count, the results are stored and ready to go. But here's the kicker. They also handle incremental updates. That means as new data rolls in, they only update what's changed, not the whole data set. Hang on, because this part's super important. This efficiency keeps performance high while ensuring correctness. No recalculating everything from scratch every time. Perfect for analytics where you want reliability and speed in a production-grade ETL pipeline. Now let's shift over to SQL views. These compute results on demand, which sounds nice, but it's a double-edged sword. Every time someone queries it, it recalculates everything, filtering, sorting, the whole deal. That's fine for small data sets or one-off checks, but for a materialized view that needs to stay consistent and fast with new data, not so much. There's no caching and no automatic updates, so you'd be stuck manually refreshing or rewriting queries. You might be thinking, can't I just tweak it to work? Maybe, but it's not designed for that kind of efficiency or correctness over time. Next up, streaming tables only. These are built for continuous ingestion, data streaming in real time, which is awesome for live updates. But here's the catch. They don't aggregate or sort results automatically. You'd have to add that logic yourself, and even then, they're not really set up to cache or handle incremental updates like a materialized view needs. They're more about keeping the data flowing than optimizing for analytics queries. So while they're great for certain use cases, they don't quite match what we're after here. Finally, we've got static delta tables with full refresh. These are solid for storing data, and they can handle filtering and sorting if you set it up. But the full refresh part, that's a red flag. Every time new data comes in, you'd have to recalculate the entire data set, missing years filtered out, artists sorted by song count, the works. That increased operational overhead and latency, it's a killer for efficiency. You might be wondering why this happens, and it's because they're designed for stability, not dynamic updates. Not ideal for our scenario. So what does this really mean for you? For the Databricks exam, you need to spot the option that balances efficiency and correctness with incremental updates. Materialized views stand out here. They're built for this exact purpose. They cache the results, update incrementally, and support the filtering and sorting we need. It's like having a smart assistant who keeps your analytics ready without you lifting a finger every time new data arrives. Let's walk through it again. We're filtering out missing years and sorting by song count. Materialized views handle that up front. New data comes in, they update just the changes, keeping everything correct and fast. SQL views and static delta tables force full recalculations, which kills efficiency. Streaming tables don't sort or aggregate on their own. It's clear materialized views are the winner for this Lakeflow declarative pipeline setup. All right. In continuation to the previous parts, Let's look at question number 14. Imagine you're a data provider in an Azure Databricks workspace. Everything's set up with Unity Catalog, so you've got governance, auditing, all the good stuff. Now you've got an external partner, maybe they're a consultant, maybe a client, who needs access to your data. Here's the catch. They don't have a Databricks workspace. So the question becomes, how do you share your data securely and efficiently? Here are the options you might be considering. Use the Databricks to Databricks sharing protocol to allow your external partner read-only access. Use the Delta sharing open sharing protocol and create a recipient with a long-lived bearer token for authentication. Export the tables to CSV files and share them via a secure file transfer protocol outside Databricks. Grant the external partner admin access to your Unity Catalog workspace so they can query the data directly. Okay, take a moment and think about it. Which one makes the most sense? Hang on, because this part's super important. So why can't we just use the Databricks to Databricks sharing protocol? Well, you might be wondering why this happens, but this method is great if both workspaces are Databricks and both are using Unity Catalog. That's a pretty big if. Our scenario says the partner doesn't use Databricks at all. So while this protocol is fantastic for internal or partner-to-partner sharing inside the Databricks ecosystem, it won't work here. Now, what about exporting tables to CSV? This is the old school, let's just dump the data and email it approach. It might seem simple at first glance, right? But here's the thing, exporting to CSV is not scalable, especially if you're dealing with large data sets. And let's not forget governance. How do you track who has access, who opened the file, or if the data got altered? You can't. Auditability goes out the window. So not ideal for a professional environment where data compliance matters. And here's the option that might make your stomach drop a little: granting admin access to the external partner. You might be thinking, well, if they have admin, they can just get in and query whatever they need. True, but here's the problem. It's a huge security risk. You're basically handing over the keys to the kingdom. Admin access means they can see and change things far beyond just the tables you want to share. This violates the principle of least privilege, which is a cornerstone of cloud security. So yeah, not a good idea. So what does this really mean for you? The solution here is Delta sharing. Delta sharing is an open protocol designed specifically for scenarios like this. With Delta sharing, you can share data securely with anyone, whether they're using Databricks or not. That's huge. You create a recipient object for the external partner, and then you authenticate using either a bearer token or OpenID Connect. The bearer token is especially neat because it comes with a credential file and an activation link. You can share that safely, and the recipient gets read-only access. No need for them to set up a Databricks workspace, no admin access, no emailing giant CSV files around. It's secure, scalable, and auditable. Let's break that down together. Think of it like giving someone a key card that only opens one door for a limited set of actions. You don't hand them the master key to the building. They can only access the data you've shared, and you can track usage, revoke access, or rotate tokens whenever needed. And because it's protocol-based, the external partner can pull the data into any system they're using: Python, R, SQL, even Spark, as long as it supports Delta sharing. Now, here's a little tip. If you're prepping for Databricks exams or any cloud certification, questions like this often test your understanding of secure data sharing and access control. The key takeaway here isn't just knowing Delta sharing exists, it's understanding why it's the right choice, especially compared to seemingly simpler but less secure methods like CSV exports or admin access. All right, to wrap this up, remember, Databricks to Databricks sharing only works if both parties are on Databricks. CSV exports, scales poorly, no auditing, risky. Admin access, big no-no, security nightmare. Delta sharing with bearer token, the winner. Secure, auditable, cross-platform.